Let's look at comparing the phase of two sinusoidal waveforms. To do that, we have to remember some rules. Both of the waveforms, the sine waves, have to be expressed either as sine waves or as cosine waves. We know that there's a phase shift of 90 degrees between a sine and a cosine. So we want to express them both as one or the other. And both must have positive amplitudes in order to compare the phase. And they both must have the same frequency. So for example, we cannot compare the sine of 3t plus 30 degrees with cosine 3t plus 30 degrees. We can't compare these 30 degrees. In order to compare them, we first have to convert either sine to cosine or cosine to sine, and then we can compare those two phase angles. We can't compare this 30 degrees to this 60 degrees because this amplitude is negative. So we have, typically what we want to do is we want to convert, we always want to have a positive amplitude, so we want to convert this negative amplitude to positive. In this third example, since this radian frequency is 3 radians per second and this is 4 radians per second, the phase difference between them makes no difference. So we never compare the phase angle of two different frequencies. So if we look at this example, if we want to compare this cosine sine to cosine, we can convert this cosine to a sine, and then we'll compare the phase to this 30 degrees. We know that the cosine, for example, of omega t, since cosine leads the sine, that's equal to our sine of omega t plus 90 degrees. So then this is going to be equal to our cosine, where our omega is 3t, and then we'll do the plus 90 degrees, but we have to still add back in that 30 degrees, so we end up with 120 degrees. So these are the two phase angles that we'll compare, and we can see then, whoops, not this one. These are the two phase angles that we'll compare. They happen to be the same, 30 degrees. So we can see that this one's leading, 120 degrees is leading 30 degrees by 90 degrees. So we can say our cosine of 3t plus 30 degrees is leading sine of 3t plus 30 degrees by 90 degrees. And that makes sense because we know the cosine leads the sine by 90 degrees. If we looked at the second one where we have this negative, we want to convert that, we can say this is equal to 80 sine of 3t plus 60 degrees, and then we have to do the plus or minus 180 degrees. So when we're choosing, which do we choose, the plus or the minus? Well, what was chosen here is we chose the minus 180 degrees. So we subtract 180 degrees so that this final 120 degrees, that's in the range of, we typically want to keep that angle theta, we want that to be between 180 degrees and negative 180 degrees. So then we can say that in fact then is lagging, or that negative 120 is lagging this 30 by 150 degrees. And lastly, we can't compare these two. No meaningful context because they have different frequencies. So converting sines to cosines, it's the same function with a 90-degree phase shift. So we say the sine lags the cosine by 90 degrees. So if we're converting a sine to a cosine, we want to subtract the 90 degrees. Cosine leads sine by 90 degrees, so we're converting cosine to sine. We want to add the 90 degrees. So what we're considering as zero time is relative, but if we look at these two functions, this light green function is leading the red function by what looks like our pi over 2 or by the 90 degrees. And again, you could use radians, pi over 2, but engineers, we typically use degrees. So for converting a negative sign is going to be sine plus or minus 80 degrees. A negative cosine is going to be the cosine omega t plus or minus 80 degrees. If we're converting sine to cosine, then a negative sine would be a cosine of omega t plus 90 degrees, but the positive sign, we subtract the 90 degrees. Again, if we have the negative cosine, then we can convert that to cosine omega t minus 90 degrees. Or you can do it in 2 steps to make sure you don't make a mistake there. Again, a negative 180 degree phase shift, or negative becomes 180 degree phase shift. So if we have a negative sine omega t plus 40 degrees, we're going to subtract the 180 degrees. So our phase angle is between negative 180 degrees and 180 degrees. That's the convention, is we keep that phase angle in this range. So when we have the negative sine omega t minus 40 degrees, then we are going to add, this should be a minus here. That's an error. This should be a minus right there, because that's a minus there, right? Where what we're doing is we're adding the 180 degrees, so we end up with a positive. So in both of these two cases, we end up with something within our convention range. So let's look at an example here. If we want to compare the phase of V1 and V2, so V1 has a radiant frequency of 5 radians per second, as does V2, so we can compare them both. V1 is a cosine function, V2 is a sine function. They have different amplitudes. We don't care about those because we're just comparing the phase shift. So now we can go ahead and compare them, but we need to either convert the cosine to a sine or the sine to a cosine. So if we convert the cosine to a sine, then we add the 90 degrees. So we have we converted cosine to sine, and then we added the 90 degrees. It's still our omega is still 5 radians per second, so we still have 5t, and we still have to add that 30 degrees to it. So we end up with sine 5t plus 120 degrees. We could also convert the sine to a cosine, so this would equal our Vm2 cosine. By converting to cosine, then we still have our 5t, we still have our minus 10 degrees, but when we converted sine to cosine, then we have to subtract 90 degrees, and this ends up equaling Vm2 cosine of 5t minus 100 degrees. So in both cases, we end up, right, so that here we compare the minus 100 degrees to plus 30 degrees, and we can see that our V1 is leading by 130 degrees, and in this case, we're comparing 120 degrees to the negative 10 degrees, and V1 is leading by 130 degrees. We could also say that V1 lags V2 by 260 degrees, but again, normally our convention is we want that to be less than or equal to 180 degrees when we're doing that. So we can look at this also on a phase chart where we have our 0 degrees, and up here we only have 0 degrees labeled, but our convention is that we go counterclockwise. So this is the 90 degrees, 180 degrees, 270 degrees down here, or pi over 2, pi, 3 pi over 2. So this is the direction that we move through time. As we move through time, and we see that V2 is always going to be lagging V1 as it circulates through time on this phase chart. Again, so on this phase chart here, the magnitude of each sine voltage is corresponding to the length of the vector or the arrow here, and the phase angle is represented with respect to the positive x-axis. So we see it's V1 leading by this 130 degrees, or V2 lagging by the 130 degrees. Whoops. Again, arguably we could say V2 leads V1 by 260 degrees. That's also an error. That should be 260 degrees. But we want to stick with our convention. So again, that's throughout time, V1 is going to lead by 100 plus 30 degrees, or 130 degrees, as these vectors rotate counterclockwise through time. as we increase time. All right, that's it for this video.